Welcome to The Explainer. I am absolutely thrilled you're joining us today because, well, we are tackling something incredibly powerful. If you've been wanting to completely demystify how AI and machine learning actually make predictions, you are in exactly the right place. You know, we constantly hear buzzwords like algorithms, models, and AI just thrown around everywhere, right? But today, we're actually popping the hood. We're going to see exactly how these systems use data to predict the future. It's totally fascinating, it's highly logical, and by the end of this explainer, you're going to fully understand the core engine running practical machine learning.
Just think about this for a second. How does a computer look at, say, 10,000 past home sales with all their crazy variations in size, age, location, and then instantly predict the exact price of a totally new listing? Real-life data is messy, it's chaotic. Guessing unknown values feels like it should require some deep human intuition or, I don't know, some kind of AI magic. But here's the secret. There's zero magic involved. There's only a method. It's a highly structured mathematical process that takes all that chaos and turns it into precise numerical predictions. And today, we're going to break this seemingly complex concept down into 5 completely digestible steps. So here is our roadmap. First, the big idea. Lines. Second, finding the best fit. Third, the math behind predictions. Fourth, real models, real data. And finally, number 5, 2 regressions you meet daily. Okay, let's dive right into this. Section 1, the big idea, lines. Let's strip away all the heavy jargon for a minute. Before we even touch Python code or any complex equations, we really have to grasp the basic philosophy of what a regression model actually is. At its core, regression is simply prediction with a line. That's it. You take known inputs and you map them to unknown outputs. So you give the model examples. Maybe your input is the square footage of a house, and you show the model the output, which is the house price. Or maybe you take hours studied and map that to an exam score, or marketing spend mapped to Q4 revenue. Regression just finds the best line to map those inputs to outputs. And once you have that line, you can use it to predict the output for entirely new inputs you've never even seen before. Honestly, that is the whole game right there. I really want to anchor this abstract idea to your everyday life. Literally, every business analytics dashboard runs a regression model exactly like this under the hood. Whether a company is forecasting its sales for the next quarter, trying to predict how many clicks an ad is going to get, or just estimating your food delivery time, they are using regression. It is the absolute workhorse of practical machine learning. But that brings up a really good question, doesn't it? If the whole game is just drawing a line to connect inputs to outputs, how on earth do we know exactly where to put that line? That brings us to section 2, finding the best fit. So imagine you're looking at a graph. You've got 15 data points scattered all across it, showing study hours versus exam scores. Now, if you draw a straight line right through that scatter plot, it obviously won't hit every single dot perfectly, right? It's just not possible. The physical distance between what actually happened, the actual dot, and what your line guessed, the line itself, has a very specific name in data science. It's called a residual. I know, fancy word, but a residual is literally just the gap. It's the physical difference between a real data point and your prediction line. Now, we can't just add up those gaps to see how well we did. Think about it. If we guess too high on one point and then too low on another, a positive gap and a negative gap would just cancel each other out. It would make our line look totally perfect when it's absolutely not. So what do? We use what are called squared errors. We simply square the gap. And this does 2 totally brilliant things. First off, it makes all the errors positive, so no more canceling out. And second, squaring a number makes it grow exponentially, right? So this heavily penalizes wild guesses. Basically, the bigger the square, the worse your prediction. So our ultimate goal here is simply to minimize the total size of all those squares. Let's say you were to manually drag a line around a scatter plot of those 15 students, and you're trying to shrink those squared errors as much as you possibly can. Eventually, you'd hit a hard mathematical limit. For our simulated class dataset, that limit happens to be exactly 23.1. That number is the optimal mean squared error. And what this proves is that fitting a line isn't just about subjective human judgment or eyeballing it. There is a definitive mathematical best answer that we're aiming for, the point where the total error is literally as small as it can possibly be. But now that we know what the target is, how does a computer actually find that perfect line? Because it's definitely not manually dragging it around like we just imagined. Let's get into it in section 3, the math behind predictions. First things first, I want to reassure you right now, you do not need to know calculus to understand this part. We can deconstruct the math into a super accessible recipe. It really just comes down to 3 simple steps.
Step 1 is the old familiar line equation, y equals mx plus b. Remember that from school? A line in a 2D space is defined by just two numbers. M is the slope. That tells you how steep the line is, like how many extra points you gain on an exam for every single extra hour you study. And b is the intercept. That's your starting point on the y-axis, kind of like your base exam score if you studied for absolutely 0 hours. Step 2 is measuring the error, using those squared gaps we just talked about. And then step 3. This is where the magic actually happens, finding the exact m and b that minimize that error. Now, under the hood, calculus gives us an exact, perfect formula for this, so there's no guessing involved, no trial and error. The optimal slope and intercept can be computed in one single shot. And honestly, that is exactly why linear regression is so incredibly fast for computers to run.
Moving right along to Section 4, Real Models, Real Data. Now, what's really interesting here is that we're finally graduating from the theory of hand-drawn lines on a basic 2D graph, and we're stepping out into the real world. Let's crank up the complexity a bit. We're no longer just comparing one input like study hours to one output. We're going to look at a synthetic housing data set of 500 homes, and we're going to predict the price using 3 distinct features simultaneously. We're looking at square footage, the number of bedrooms, and the age of the house. Now, in this specific dataset, the true underlying relationship is that a house gains about $150 for every square foot, $35,000 per bedroom, and it loses $1,200 for every year of age. This is what we call a multivariable model, and it is exactly how real-world supervised learning problems are actually set up.
So, how do we train a model to just figure out all those relationships on its own? Well, we follow a universal machine learning loop. First off, we load the data. Second, we split it. Usually we keep about 80% of the data for training, and we physically hide the remaining 20% so we can test the model later. Third, we train, or fit, the model. In Python using skitlearn, this takes like 3 lines of code. It's incredibly simple. Fitting just means the computer is automatically finding those mathematical coefficients, the slopes and intercept for all 3 variables all at once. Fourth, we evaluate the model on that hidden 20% of data to see how it did. And finally, we predict. We can now plug in a brand new house's features, and our model will instantly spit out a precise price estimate.
And I have to point out, this brilliantly illustrates the true scale of what you're learning today. The exact same pattern is how every supervised ML model is used, from our little 3-feature housing model all the way up to a 100 billion parameter large language model. Seriously, how incredible is that? Whether you're predicting a simple house price or you're interacting with a massive AI that predicts the very next word in a sentence, the fundamental pattern, load, split, fit, evaluate, predict, remains exactly the same across the board. You are literally looking at the foundational architecture of AI here. All right, let's zoom out a bit and look at the bigger picture of how this concept branches out.
Which brings us to our final section, Section 5, 2 regressions you meet daily. While predicting a continuous number, like a house price, is obviously super useful, it is definitely not the only way regression is used out in the wild. There are really 2 main flavors you're going to encounter. So on one side, we have linear regression. This is everything we've been talking about so far. It predicts a continuous number. It answers questions like how much, how long, or how many. Think house prices or estimated delivery times. But on the other side, we have logistic regression. Now, despite actually having the word regression right in the name, this algorithm doesn't predict a continuous number at all. It predicts a category or a probability between 0 and 1. So it answers questions like, will they, or is it a yes or no? And surprisingly enough, logistic regression is actually the most used classification algorithm in the entire world. It's exactly what runs the spam detection in your email inbox, it predicts whether a user is going to click an ad, and it even calculates the probability of a loan default. But listen, regardless of which type you end up using, the absolutely crucial takeaway here is that a model is only ever as good as its predictions on unseen data. Evaluation matters immensely. When we evaluate a linear model, we look at a special metric called the R-squared score, which basically just measures the proportion of variance our model can explain. A perfect score is 1.0, and generally speaking, anything above a 0.85 means you've got some really strong predictions. If you visualize it and plot your predicted prices against the actual real-world prices, you want all those dots clustered super tightly along a nice diagonal line. But inevitably, you're going to have some scattered points that stray way far out from that line. And those outliers, those represent your model's biggest mistakes. Which leads me to leave you with one final, pretty provocative thought. If your model's points are scattered far away from the line, what's missing? And more importantly, how are you going to find it? You see, when regression fails, it's almost always a massive clue. Are you missing some key features? Take our house example. Maybe you accurately measured the square footage, but you totally missed the fact that the house is sitting right next to a super noisy highway.
Or perhaps there are complex non-linear effects going on that a simple straight line just can't capture. Honestly, diving in and exploring those mistakes is where the real art of data science actually begins. It's exactly what pushes developers to explore much more advanced algorithms. But for now, you've got it. You understand the core engine. You know exactly how simple lines can be used to predict the future. Thank you so much for joining me for this explainer, and hey, keep learning.